Greetings, young students. Hope you're doing well. I want to talk to you today about linear inequalities. Before we get started, well, we are started, but as we start, let me really reinforce or clarify something. When I say linear inequalities, this is what one looks like. So I shade that. This is a linear inequality. And I will tell you that that used to confuse me when I was a teenager, because I thought a linear inequality looked like this at the bottom. You see me working on this number line? Something like this. I used to think those were a little pathetic. I didn't understand the point of those. But this is the one on the bottom, this number line, that is not a linear inequality. This is a one variable inequality. And we'll probably hit those again before the end of the semester, but they're rather simple, except there are some compound ones we're going to work on, but that's a one variable inequality. The one that we're looking at top is linear because the graph is a line. So let me give you a little bit more vocabulary while we're here. This is not really a line either. That is called a boundary. There are two types of boundaries when you talk about linear inequality. There's the dashed, which look like that, of course. And then there's a solid boundary, which, of course, looks like that. When you have a dashed boundary, it is a result of graphing something that has a greater than or a less than sign. And I remember, by the way, sidebar, I remember the less than sign because it looks like an L that's kind of been squished, yes? So that's what a less than sign is. The other one is greater. That aside, the solid boundary is because you have greater than, there's a less than or equal to, or greater than or equal to. When you shade one of these linear inequalities, the area that you shaded is called the half plane. And often students will say, that's not a half plane, that's like maybe an eighth or a tenth. But if you think about the fact that this grid goes on into infinity and beyond, it is indeed half a plane. Yes? Yes, Miss Wilson? Yes. Okay, and another thing I want to accentuate is this. If you have a dashed boundary, what that symbolizes is that the points on that boundary, the coordinates on the boundary, are not solutions. Let me restate it this way. The dashed boundary does not include, the solutions do not include the points intercepted on that boundary. It's exclusive. It's like snobby girls, exclusive. Whereas a solid boundary, the points on the boundary, are included in a solution. Okay, so there we have it, a little vocabulary, a little clarification about what we're working with today, which is the third thing I haven't even mentioned. This is a system of inequalities as opposed to a system of equations, system of inequalities. We're going to graph a few, and I'm going to make a few points on this first one. Oh, I'm so glad it's x equals, because those are so easy to graph. X equals or x greater is simply a vertical line, yeah? So if this one I'm going to do in pink, x is greater than -1, I just go to the -1 and I draw it. And I need to know which way to shade. Well, if it's greater than -1, then of course it's going to be everything on this side. And I don't shade everything, it looks too messy, I just do little stripes. But you are welcome to. On x is less than 1, I go to the 1. Oh, I'm sorry, that is so crooked. My cat is on my lap. It's her fault. So then I'm going to shade everything on this side because it says x is less than 1. My solution set is simply this corridor. It doesn't include everything on those lines, on those boundaries, excuse me. It is everything within that corridor. Any ordered pair I pick inside there will satisfy both those equations, or inequations, if you will. Let's look at another problem. This one is y is greater than 2. So I go to the 2. Y is always a vertical line. It's going to be y, everything greater than that. So I shade this direction. And then on the other one, it's y is less than 3, but this is a dashed boundary, yes. And this is the red one, and it's everything down from there. So the only solutions that will satisfy both these are the ones within that are shaded and represented by both areas of shading. Let's move on because we need to. On this one, even though I know I could really just do the, you know what, I could do the xy intercepts, I will. Usually I just change it to slope intercept. Okay, if I do away with the y, x is 1, right? And if I do away x plus y, it's greater than 1. If I do away with the x, turn it to 0, the y is 1. So here's my equation, and it is a dashed boundary. Where do I shade? Here's what I do. I pick a point that's away from the line, that's easy to deal with. I'm going to try 0, 0. If I put 0 in for x and 0 in for y, and I put it in that equation, does the equation remain true? Well, if x is 0 and y is 0, that makes it 0 is greater than 1. Is 0 greater than 1? No, it's not. So if this 0, 0 doesn't work, boys and girls, then nothing on that side works, and you better shade this way. There we go. Okay, now let's do the other one. X. This is the same thing as x is equal to y with shading. So y is equal to x, or x is equal to y, is the same thing as y. It's x plus 0 is less than y, right? Or greater than y. So it's a y-intercept of 0, slope of 1. It's solid. Like that. Now this time I'm not going to check 0, 0 because it's too close to that line. Matter of fact, it's on the line, and that wouldn't help me to shade. So I'm going to pick a point away from that. I think I'll do -3, 0. So when x is -3, y is 0. I'm going to try this point to see if this is a direction in which I should shade. So I put -3 in for x. I put 0 in for y. Is -3 less than 0? Hey, it is, right? That means that I need to shade everything on that side of the green line. That means my area of intersection for both graphs is right there. There's my little area that all points inside there will satisfy both the solutions. Okay, this one, y is greater than 2. So I go to 2. It's a solid line. Y is greater than. I'd like you to be pretty fast on your graphing. You need to be. And here, I think I could do x and y intercepts. If I turn the y to 0, the x is -3, right? So there's a point. I should do it in a different color. There's a point. And now, if I turn the x to 0, the y is what? -3. Wow, it barely fits on here, doesn't it? And it's a solid. And now I'm going to test a point. I think I'll test 0, 0. If I had 0 plus 0, is that less than or equal to -3? Is 0 less than or equal to -3? Is 0 more than -3? Yes, it's more. That means that 0, 0 can't be a solution, so I must shade on this side, rendering this area right here my little solution corridor. So, you know how to graph them. It takes some practice to be good at it. Now you get questions like this, and usually students will call me over and say they only graphed part of this. They don't have two areas and show the intersection. The shaded area you see is the area of intersection for both graphs. And all you have to do when you're given problems like this, it says, is 3, 0 a solution? Look at that. Is that included in both areas? Yeah. So this is a solution. Look at the 2, 2. Okay, 2, 2 is a solution. Now, listen, if that was not a solid boundary, if that was a dashed boundary, it would not be a solution because the solutions are not included on the points that are intersected by a dashed boundary. But because indeed it is a solid boundary, that 2, 2 is a solution there. Let's look at this one. Negative 2, 2. Oh, I'm glad they used one like that to show the contrast. Now the negative 2, positive 2 coordinate shows up smack dab on that dashed line. That means, because a dashed line means we don't include these points, we're snobby, then that is a big no. Okay, I hate these matching graphs. I'm just going to tell you right now, I'm not fond of them. These are, usually they're really easy because you can just look at the equations and tell by the dash and the solid what's going on, and I loathe matching. So here's how I'm going to approach this. I'm sure I'm going to get this wrong. On this one, the solution is negative 3, 0. The solution isn't negative 3, 0 on those two, is it? So I need to see which one A will fit into. So if I use negative 3 for x, is negative 3 greater than negative 1? No, it's not. So number 4 cannot be A. Let's see if this can be A. I'm going to put negative 3 right here. Is negative 3 less than negative 1? Yeah, negative 3 is less than negative 1, right? So this has the potential to be the right. Let me try it in the y. If I have negative 3 for x and I have 0 for y, that would make it 0 plus 3 halves. I'm multiplying negative 3 by negative 1 half. Is less than or equal to 2, 3. Okay, that's true. So I think 5. I think A is 5. This graph goes there. Okay. And sure enough, that must be true. Because look, if I put negative 3 in here for x, if I tried this equation right here, negative 3 is not greater than negative 1. So this cannot be A. So I think 5 was a good pick with A. So I know what A belongs to. I don't want to use it again, so I'm going to put 5 there. Because it belongs to number 5, and 5 belongs to letter A. So now let's do this one. I want to use a point. Oops, I didn't mean to take that A out. I want to use a point here on this graph that is not as... I don't want to pick a point that would solve for both of them. For instance, I'm not going to use a point like this because it'll fit both equations, yes? I'm going to use one that's a little bit more exclusive. So I'm going to go to C, and I'm going to use 0, 0, because 0, 0 on C is not a solution on B. So I'm going to go to 4, and I'm going to go to 6, and I'm going to try my 0, 0. Is 0 greater than negative 1? Yeah, but this is the same equation. Okay, so 0 is greater than negative 1. So 0, 0 works in the bottom one. I'm going to have to try the top. If I use 0, 0 in the top, 0 times 1/2 is 0, plus 0 is greater than 3. Oh no, that doesn't work. So C cannot be 4, and it can't be 5. So C must be 6. I want to check it. Is 0 less than 0 plus 3? Yes. Okay, so if this is C and this is A, this is B. I really do hate matching. I shouldn't say hate, should I? Okay, so, well, as long as it's not people, it's okay. All right, that concludes our inequalities. We'll have this practice in class. You guys take care.